The National Electrical Code, or NEC, does not specifically prohibit splitting a multi-wire branch circuit into two separate cables, effectively dedicating one cable to phase A and the other to phase B. However, several key considerations must be adhered to when implementing such a configuration. Firstly, both cables must be of identical size and type. This requirement ensures that the current carrying capacity and insulation properties are consistent across the circuit, preventing imbalances and potential overloading of one conductor over another. Secondly, the cables must be installed within the same raceway or cable tray. This proximity helps to ensure that both cables experience similar environmental conditions, such as temperature, and that any inductive effects are balanced. This is crucial for minimizing voltage drop and maintaining circuit integrity. Thirdly, the cables must terminate within the same panel board or electrical enclosure. This ensures that both phases of the multi-wire branch circuit are effectively managed and protected by the same overcurrent protection devices. In scenarios where an existing circuit needs modification, such as locating and replacing outdated knob and tube wiring, commonly referred to as K&T, followed by adding a new circuit using an unused conductor, such as the red conductor in a 12-3 non-metallic sheath cable, this method is permissible under the NEC. Regarding overcurrent protection devices, or OCTs, for multi-wire branch circuits, the NEC allows the use of individual single-pole circuit breakers equipped with handle ties. These handle ties ensure that if one circuit breaker trips due to an overcurrent condition, the other circuit breaker also trips simultaneously, disconnecting both phases of the circuit. While single-pole circuit breakers with handle ties are permitted, a two-pole circuit breaker is often recommended as a superior choice for this application. The two-pole circuit breaker provides inherent simultaneous tripping, eliminating the reliance on handle ties, which can sometimes fail to operate correctly. Furthermore, a two-pole circuit breaker offers better protection against imbalanced loads and certain types of fault conditions. It is crucial to recognize that the NEC does not mandate the use of a two-pole circuit breaker for multi-wire branch circuits. The code provides the option of using single-pole circuit breakers with handle ties as an acceptable alternative. However, employing a two-pole circuit breaker generally enhances the overall safety and reliability of the circuit. In summary, when splitting a multi-wire branch circuit into separate cables, adherence to the NEC guidelines is paramount. These guidelines include ensuring that the cables are of the same size and type, running them together in the same raceway or cable tray, and terminating them within the same electrical enclosure. While single-pole circuit breakers with handle ties are permissible for overcurrent protection, a two-pole circuit breaker is often the preferred option due to its enhanced protection capabilities and inherent simultaneous tripping action. The NEC addresses various aspects of electrical installations, including the protection of conductors. Section 240. 20.1 discusses the requirements for overcurrent protection devices in specifically grounded systems. It states that overcurrent protection shall be provided in each ungrounded conductor. This means that each phase of a multi-wire branch circuit must have its own overcurrent protection device, such as a circuit breaker or fuse. The NEC also permits the use of single-pole overcurrent devices with handle ties for multi-wire branch circuits. Handle ties are devices that connect the handles of two or more single-pole circuit breakers together so that if one breaker trips, all the breakers connected by the handle tie will also trip. This ensures that all the ungrounded conductors of the multi-wire branch circuit are disconnected simultaneously in the event of an overcurrent condition. Section 240.2 addresses the protection of tap conductors. Tap conductors are short conductors that are connected to a larger feeder or branch circuit conductor. The NEC contains specific rules for the protection of tap conductors, which are designed to prevent them from being overloaded. However, if the conductors are not considered tap conductors, then these rules do not apply. If the circuit is continued using the same gauge wire, such as 12 American wire gauge or AUG, the conductors are not considered tap conductors, and Section 240.21 does not apply. The NEC provides guidelines for the protection of electrical equipment. These guidelines are intended to prevent damage to equipment and to protect people from electrical hazards. Chapter 3 of the NEC covers wiring methods and materials. This chapter provides detailed requirements for the types of wiring methods that are permitted in various applications. It also covers the types of materials that must be used for electrical wiring. Chapter 4 of the NEC covers equipment for general use. This chapter provides requirements for the installation and use of various types of electrical equipment such as receptacles, switches, and lighting fixtures. The NEC requires that all electrical work be performed in a neat and workmanlike manner. This means that the work must be done in a way that is safe, efficient, and aesthetically pleasing. The NEC is a comprehensive set of rules and regulations that govern the installation and maintenance of electrical systems. It is important to consult the NEC when planning or performing any electrical work. Article 100 of the NEC provides definitions for terms used throughout the code. This ensures that everyone using the code has a common understanding of the terminology. Article 110 covers general requirements for electrical installations. This includes requirements for working space around electrical equipment, guarding of live parts, and identification of conductors. Article 200 covers the use and identification of grounded conductors. This article specifies how grounded conductors, commonly referred to as neutral conductors, must be identified and connected in electrical systems. Article 210 covers branch circuits. This includes requirements for the number and type of branch circuits that are required in various occupancies, as well as the overcurrent protection requirements for branch circuits. Article 215 covers feeders. Feeders are the conductors that carry power from the service equipment to the branch circuits. This article includes requirements for the size and overcurrent protection of feeders. Article 220 covers branch circuit, feeder, and service calculations. This article provides the methods for calculating the load on branch circuits, feeders, and services to ensure that they are adequately sized. Article 230 covers services. The service is the connection between the utility power supply and the building's electrical system. This article includes requirements for the size, overcurrent protection, and grounding of services. Article 240 covers overcurrent protection. This article specifies the requirements for overcurrent protection devices, such as circuit breakers and fuses, to protect conductors and equipment from overcurrent conditions. Article 250 covers grounding and bonding. Grounding and bonding are essential for electrical safety. This article specifies the requirements for grounding electrical systems and bonding metal parts to ensure a low impedance path for fault current. Article 300 covers general requirements for wiring methods and materials. This includes requirements for the installation of raceways, cables, and conductors. Article 310 covers conductors for general wiring. This article specifies the requirements for the types of conductors that are permitted for use in various applications, as well as their ampacity ratings. Article 314 covers outlet device, pull, and junction boxes, conduit bodies, fittings, and hand-tool enclosures. This article specifies the requirements for the installation of these enclosures to ensure that they are properly sized and installed. Article 320 covers armored cable. Armored cable, commonly referred to as AC cable, is a type of cable that has a metal armor to protect the conductors. This article specifies the requirements for the installation of AC cable. Article 330 covers metal-clad cable. Metal-clad cable, commonly referred to as MC cable, is a type of cable that has a metal sheath to protect the conductors. This article specifies the requirements for the installation of MC cable. Article 334 covers non-metallic sheathed cable. Non-metallic sheathed cable, commonly referred to as NM cable, is a type of cable that has a non-metallic outer jacket. This article specifies the requirements for the installation of NM cable. Article 340 covers underground feeder and branch circuit cable. This article specifies the requirements for the installation of underground feeder and branch circuit cable. Article 350 covers liquid-tight flexible metal conduit. This article specifies the requirements for the installation of liquid-tight flexible metal conduit. Article 352 covers rigid polyvinyl chloride conduit. This article specifies the requirements for the installation of rigid polyvinyl chloride or PVC conduit. Article 358 covers electrical metallic tubing. This article specifies the requirements for the installation of electrical metallic tubing or IMT. Article 366 covers auxiliary gutters. This article specifies the requirements for the installation of auxiliary gutters. Article 370 covers cable trays. This article specifies the requirements for the installation of cable trays. Article 376 covers metal wireways. This article specifies the requirements for the installation of metal wireways. Article 386 covers surface metal raceways. This article specifies the requirements for the installation of surface metal raceways. Article 392 covers cable bus. This article specifies the requirements for the installation of cable bus. The NEC provides tables that provide information on conductor ampacity. Table 310.15b16 provides the allowable ampacities of insulated conductors rated up to and including 2000 volts. This table takes into account the conductor size, insulation type, and ambient temperature. When using Table 310.15b16, it is important to apply any applicable correction factors. Correction factors are used to adjust the ampacity of a conductor for ambient temperatures that are higher than 30 degrees Celsius or for situations where more than 3 current-carrying conductors are installed in a raceway or cable. The NEC provides examples of how to calculate branch circuit, feeder, and service loads. These examples can be helpful in understanding how to apply the load calculation methods in Article 220. Example D3 in Annex D of the NEC provides an example of a dwelling unit calculation. This example shows how to calculate the general lighting load, small appliance branch circuit load, laundry branch circuit load, and appliance loads for a dwelling unit. Example D5E in Annex D of the NEC provides an example of a multifamily dwelling calculation. This example shows how to calculate the service load for a multifamily dwelling. It includes calculations for the general lighting load, appliance load, heating and air conditioning load, and electric vehicle charging load. Example date in Annex D of the NEC provides an example of a restaurant calculation. This example shows how to calculate the service load for a restaurant. It includes calculations for the lighting load, receptacle load, cooking equipment load, and air conditioning load. In addition to the NEC, local codes and regulations may also apply to electrical installations. It is important to check with the local authorities to determine what codes and regulations are in effect in a specific area. Furthermore, it is essential to use listed or labeled equipment when performing electrical work. Listed or labeled equipment has been tested and certified by a recognized testing laboratory to meet safety standards. Using listed or labeled equipment helps to ensure that the electrical system is safe and reliable. The electrical work should only be performed by qualified individuals. Qualified individuals have the training and experience necessary to perform electrical work safely and in accordance with the NEC and other applicable codes and regulations. When working on electrical systems, it is important to always energize the circuit before starting work. This can be done by turning off the circuit breaker or removing the fuse that supplies power to the circuit. After de-energizing the circuit, it is important to test the circuit to make sure that it is de-energized. This can be done using a voltage tester. It is also important to use appropriate personal protective equipment, or PPE, when working on electrical systems. PPE may include safety glasses, rubber gloves, and insulated tools. The NEC is updated every 3 years. It is important to stay up to date on the latest edition of the NEC to ensure that electrical work is being performed in accordance with the current code requirements. Continuing education courses are available to help electricians and other electrical professionals stay up to date on the NEC and other electrical topics. These courses can provide valuable information on new technologies, code changes, and best practices for electrical installations. Many organizations offer electrical safety training programs. These programs can help individuals learn how to work safely around electricity and how to prevent electrical accidents. Common electrical hazards include electric shock, electrocution, arc flash, and arc blast. Electric shock occurs when a person comes into contact with an energized electrical conductor. Electrocution is a fatal electric shock. Arc flash is a dangerous release of energy that occurs when an electrical fault causes a short circuit. Arc blast is a pressure wave that is created by an arc flash. These hazards can be minimized by following safe work practices and using appropriate PPE. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electric shock. GFCIs monitor the current flowing in a circuit and quickly interrupt the power if a ground fault is detected. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters, or AFCIs, are devices that are designed to protect against electrical fires. AFCIs monitor the current flowing in a circuit and quickly interrupt the power if an arc fault is detected. AFCIs are required in many locations, such as bedrooms and living rooms. Surge protective devices, or SPDs, are devices that are designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, and other events. SPD divert the surge current away from the protected equipment, preventing damage. Regular electrical inspections can help to identify potential electrical hazards and ensure that the electrical system is safe and up to code. Electrical inspection should be performed by qualified electrical inspectors. In the context of multi-wire branch circuits, the neutral conductor plays a crucial role in carrying the unbalanced load. The neutral conductor must be properly sized to handle the maximum possible unbalanced load. The NEC specifies the requirements for sizing the neutral conductor in Article 220. Section 220.61 provides guidance on calculating the neutral load for feeders and services. When dealing with nonlinear loads, such as those produced by electronic devices, the neutral conductor may carry harmonic currents which can increase the neutral current and cause overheating. In such cases, it may be necessary to increase the size of the neutral conductor or use a neutral conductor that is specifically designed to handle harmonic currents. The NEC requires that all electrical connections be made in a manner that ensures a reliable and electrically sound connection. This includes using appropriate connectors, tightening connections to the proper torque, and protecting connections from corrosion. Improper electrical connections can lead to overheating, arcing, and even fires. When working with aluminum conductors, it is important to use connectors and other materials that are specifically designed for use with aluminum. Aluminum conductors can corrode when they come into contact with dissimilar metals, such as copper. This corrosion can lead to increased resistance and overheating. Antioxidant compounds can be used to prevent corrosion when connecting aluminum conductors. The NEC provides guidelines for the proper support and securing of electrical wiring. Wiring must be supported in a manner that prevents it from sagging, chafing, or being damaged. The NEC specifies the maximum spacing between supports for various types of wiring. In addition to the technical aspects of electrical installations, it is also important to consider the aesthetic appearance of the work. The electrical work should be performed in a neat and workmanlike manner. This means that the wiring should be run in a straight and orderly fashion, and that all equipment should be installed level and plumb. The NEC is a living document that is constantly being updated to reflect changes in technology and best practices. It is important to stay informed about the latest changes to the NEC to ensure that electrical work is being performed in accordance with the current code requirements. The NEC is developed by the National Fire Protection Association, or NFPA. The NFPA is a non-profit organization that develops codes and standards to reduce the risk of fire and other hazards. The NEC is adopted by many states and local jurisdictions as the basis for their electrical codes. The NEC is a valuable resource for anyone who is involved in electrical work. It provides comprehensive guidance on how to design, install, and maintain electrical systems safely and effectively. By following the NEC, electrical professionals can help to protect people and property from electrical hazards. The NEC is not intended to be a substitute for qualified electrical training and experience. It is important to seek out qualified training and experience before attempting to perform any electrical work. Electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself and others from electrical hazards.